Welcome to Dr. Jimmy's Applied Calculus, Section 3.3. So we're going to look at some concepts. First of the infinity symbol and division by zero. So, in each case, we're going to come up with computations using the symbol infinity and possible computations when we have division by zero. So, let's consider infinity. So, pick this sequence of values, 2, 4, 6, 8, 10, and so forth. Continue that forever. And so we could think of this as growing without bound. Bigger and bigger and bigger. There's no cap on this. No matter what we do, it gets bigger. And that's our concept of infinity. I like to sort of think of it this way. Very large, larger and larger. So I sort of assign this conceptually extremely large. Now, if I were to take this set of values and do something like multiply by 3, and watch this progression, it's still large, or still has the property of becoming infinite, which gives us a way of computing with infinities. We take something large, we multiply it all by 3, it's still large. So as far as conceptual infinities, 3 infinities is still just infinite. So we're going to start using this kind of conceptual infinity arithmetic. Now if I took a negative 3 and multiplied everything, then everything gets large still, but they all have negative signs. So getting very large but becoming negative, we assign minus infinity as opposed to infinity, which we could put plus infinity. So another conceptual arithmetic would be infinity plus an infinity. So if we take large numbers, add other large numbers, we end up with large numbers. Or if we took infinity with an infinity exponent, well, that's still even larger than large, so it's still large. So we have this strange symbolic arithmetic with infinities. If we look at this progression, 2, 4, 6, 8, and so forth again, which is becoming large, and we look at the reciprocals, 1/2, 1/4, 1/6, 1/8, Oh, those are approaching 0 or becoming small. So it's this concept of 1 over very large things give very small values. And so as a basic symbolic arithmetic, 1 over infinity should come out to 0. So the reciprocal of infinity is 0. Now, that may make us ponder that then, oh, if I do the reciprocal of 0, I should get infinity. Which is almost true, but we have to look at that carefully. So if we took a progression like 1/2, 1/4, 1/8, probably should put 1/6 in there, 1/8, 1/10, and so forth. So that's very small. As we progress, so we end up at 0 in the concept of what's happening. Now if we look at these reciprocals, 2, 4, 6, 8, 10, well, they're very large, eventually larger and larger, and conceptually process of becoming infinite. So in this case, if I took the reciprocal of small, I get large. I can run into a problem if I get other small numbers, minus 1/2, minus 1/4, minus 1/6, minus 1/8. That same progression is getting very small. Or becoming very close to 0. But now reciprocals are minus 2, minus 4, minus 6, minus 8, and so forth, which are large but with negative values. So large negatives, then I get minus infinity. So, at least 1 over 0 represents infinity in some way, but it's a problem because sometimes it's looking like positive infinity, very large positive values, and other cases negative infinity. So these are very far apart, so we can't assign a single concept to 1 over 0. So, but those two cases are very distinct. And so we're going to get around that. We're going to look at 0 as having two different values. We're going to have a plus 0 and a minus 0. So as strict numbers, there's no difference between plus and minus 0. For this concept of limits and approaching, though, there is a difference. So if I have this process 1/2, 1/4, 1/8, 1/16, things are getting small, but positive values. So I'm going to indicate that things are getting close to 0 but staying positive. And a progression such as minus 1/2, minus 1/4, minus 1/8, minus 1/16. Again, it's a progression, gets closer and closer to zero, but the values are always negative. So I'm going to make a little minus symbol there to indicate. So, although it's zero at the end in both cases, I'm going to make a difference in how we're becoming small, positive or negative. And then conceptually I can write the reciprocal of zero, if I keep it positive, is plus infinity. The reciprocal of zero, if everything is negative, will be minus infinity. And 1 over 0, though, if we don't make the stipulation, we can't tell. So it will have to remain undefined. And in the case of limits and working with these creatures, the usual term is indeterminate. So some things are determinate. 1 over things getting close to 0 positive are determined to be infinity. 1 over things which are very small negatives are determined to become out to minus infinity. Just like 3 times infinity is determined to be infinity. Infinity times plus infinity is determined to be infinity. So many cases of this new symbolic arithmetic, we can assign at least conceptual values even though there's not a particular number. So, the new conceptual values using arithmetic with infinity and division by 0, we get determinate forms. So if we take something like 4 infinities, we get an infinity, any other constant. If we have a minus, then it just ends up minus infinity. Infinity plus an infinity is okay. Infinity times infinity is infinity. Infinity with an exponent of infinity. So, many things we can reason out to be there's only one conceptual value that it could have. But there are some cases which would be indeterminate. Things like infinity minus infinity can't be determined to one particular value. That's because if I took 1/2, 1/4, 1/8, and then take that and subtracted it from itself, it looks like things should be 0. Oh, bad example. Got hooked up on my last examples of division by 0. I'm sorry. Should have put 2, 4. No reciprocals, just 2, 4, 8, 16, and so forth. So, this is the concept of becoming infinite. If we take infinite and subtract this particular infinite from itself, it seems like that difference should be 0. But if I took and subtracted 2 of them, so infinity minus infinity, then this progression looks like it's going to be very large negative numbers. So we have a problem. We could actually come up with all kinds of examples of something becoming large minus other things becoming large, but the possible limiting value over here is about any number we want. That's why we can't assign a particular value to the concept of infinity minus infinity. So it's said to be indeterminate. We can't determine a single concept for that. Another indeterminate form is if we have large over large. The same thing. It depends on how big the large is, what we could get out of this. So we're not going to assign a value. We said we could possibly divide by 0 if we know the sign, but 0 over 0 won't fall into that. So there are a few forms we can't assign a particular value. They're said to be indeterminate. There are many forms, though. It's nice that we can take that form, treat it somewhat like manipulating numbers, and come up with an acceptable single possible concept out of it. So division by 0, we can assign a concept as long as we know the signs of being close to 0. But if we don't know the sign of the 0, we'll have to leave it in the indeterminate setting. Another indeterminate would be 0 times infinity. So, some things we can manipulate with infinities and division by 0 and come up with a single conceptual value. In other cases we can't. So we have to consider, is it determinate or indeterminate?